Hi everyone, today we're talking about Descartes' rule of signs. The other day we talked about the rational root theorem and we were able to create an entire list of possible roots for a polynomial if we didn't have a calculator, for example, or if the equation wasn't factorable. And what we're going to be learning about today and in our next video are just some ways that we could narrow down that giant list if we didn't have our calculators with us. So starting with Descartes' rule of signs, it's used to determine how many positive real roots and how many negative real roots a polynomial will have. So getting down to it, for positive roots, the number of positive real zeros, again, zeros, roots, solutions, x-intercepts are all the same thing, either equals the number of variations in sign, so plus to minus, occurring in the coefficients of p of x, or is less than the number of variations by a positive even integer. So this second part will make much more sense when we actually see an example. For negative roots, the number of negative real zeros either equals the number of variations in sign occurring in the coefficients of p of negative x, so we'd have to substitute negative x in place of x to figure this out, or is less than the number of variations by a positive even integer. So let's get started in an example to get these easily understood. So starting out with our first example here, take a minute, of course, to stop the video and write that down, as always. So to determine the number of positive real zeros, as we had said on the other page a second ago, you're going to look at the number of sign changes from each term in the polynomial. So you see how this coefficient is positive and then it goes to a -6? So that would account for one sign change. And then we're going from negative to positive, so that's another sign change. And then we're going from 2x to -1, so that's a third sign change. I didn't do anything in here because we're going from positive to positive. So 3 sign changes is what we have here in p of x. And so that says that p of x has either 3 positive roots, or do you remember from the previous page I was just showing you that it either has this many positive roots or is less than a number of variations by a positive even integer? So it could have 3, or what's the next positive even integer below 3? 2. So if I reduce 3 by 2, I would get 1. So 1 positive root. If this number here were 2 roots, for example, well, 2 minus 2 would be 0. So it would either be 2 or 1, or 2 or 0, excuse me. So now let's do the negative roots. So for the negative roots, we have to first find what p of negative x is. So wherever we see an x in the equation, we're going to replace it with a negative x. So negative x to the power 4 minus 6 times negative x cubed plus 8 times negative x squared minus 2 times negative x minus 1. So we have to first evaluate that out. So this will come out to positive x to the 4th plus 6x cubed plus 8x squared minus 2x minus 1. So there's our p of negative x. And now we have to look at the sign changes here. We're going from positive to positive here. That doesn't do anything for us. Positive to positive here. Doesn't do anything. Finally, we have one sign change occurring. And this is not a sign change. There's just one. So p of x has exactly 1 negative root. Now the directions say that I could also reduce this number by a positive even integer, but the only other positive even integer that I could subtract would be 2. And if I did 1 minus 2, I'd get a negative number, so that doesn't work. Okay, here I could subtract a positive even integer like 2 because the number was large enough to subtract. So now what we're going to do is we're just going to make a list. If you remember earlier in this unit, we learned that if the degree is 4, that's the biggest exponent here. So if the degree is 4, then we have at most 4 real roots. So we're going to make a list of what the roots could potentially be, because some of the roots could be imaginary roots as well. So I'm going to make a list of positive roots, negative roots, and imaginary roots. We know that they have to total to be 4. So let's say there's 3 positive roots. Well, we just learned a second ago there has to be 1 negative root. So if there's 4 roots total, then there must not be any imaginary roots here. But what if there was 1 positive root? We also know there can be only 1 negative root. So this would be 2 total. That would mean there's 2 imaginary roots in order for us to get to 4 total. You're going to have to make one of these on your test as well, okay? But it's pretty simple to do. So we'll do another example just to practice and get better at this. So in this polynomial here, now we've got a degree of 5. Okay, so there's at most 5 roots total. They could be real, they could be imaginary, but there's at most 5 total. So we're going to start with the positive roots again, and we're going to look at the sign changes in P of x. So I see that we're going from positive to negative. There's 1, 2, 3 sign changes occurring here. So similar to the last problem, we'll have 3 positive roots, or I can reduce this down by a positive even integer. So like 2. 3 minus 2 is 1 positive root. So these are my options for positive roots. Let's say there were 4 sign changes. Then I could reduce it down or subtract it down by 4 or 2. So it could be 4 roots, 2 or 0 at that point. So in order to find the negative roots, I would have to then figure out what P of negative x is. So again, replacing every x with a negative x. So once I do that, I've got to evaluate that out first before I could figure out sign changes. So this would come out to negative x to the 5th minus 3x to the 4th plus 2x squared minus x minus 1. So in looking at this polynomial here, I see 1 sign change occurring, 2 sign changes occurring. So there's either going to be 2 negative roots, or I can again reduce this by a positive even integer. So if I did 2 minus 2, there could be 0 negative roots. And so again, just like the last problem, we're going to make a list of possibilities for positive, negative, or imaginary roots. We know there's got to be 5 total. So I'll make a little plus here for our positive number of roots, a minus, an I to stand for imaginary, and total. So let's say there's 3 positive roots, for example. There could be 2 negative roots, and then that would mean there'd be 0 imaginary roots because we're already total at 5. Now, what if there were 3 positive roots, but 0 negative roots? That would leave an opening for 2 imaginary roots in order to total to 5. Now let's try the other possibility. We said that there could be one positive root. If there is one positive root and two negative roots to start, that would be 3, leaving room for 2 imaginaries in order to total of 5. And lastly, what if there is one positive root and 0 negative roots? Let me just move that up for you guys. Then that would mean there could be 4 imaginary roots total. So that is what the Descartes rule of signs says. Please make sure you can make this chart because that will be something that's definitely on your test. And your homework for tonight, page 235, 71, 73, 75. And just as a fair warning, there is a test coming at the end of next week. It'll be a test that you take at home, and you're going to send me your final answers, and that's how I'll grade it from here on out. If you've got any questions, please let me know. And if not, have a good night.